Hi, today we're going to talk about limits and continuity from an algebraic viewpoint. Let's start out with the definition. A closed form function, a closed form function is any function that can be obtained by combining constants, powers of x, exponential functions, radicals, logarithms, absolute values, trigonometric functions into a single mathematical formula. So for example, you can have f of x equals the square root of x plus 1. It combines the linear function x plus 1 and the square root function. So that's a closed form function. Another one is g of x equals 1 over x minus 1. So it combines the reciprocal function with the linear function x minus 1, puts it on the inside. A theorem says that every closed form function is continuous on its domain. So that means if f is a closed form function and f of a is defined, then we have the limit of f of x as x approaches a exists, and the limit of f of x as x approaches a is in fact equal to f of a. So an example here is consider f of x equals 1 over x. This is a closed form function and its domain is all real numbers except 0, because remember we cannot divide by 0. Okay, something else to note, f is continuous everywhere except 0. So we have that by this theorem 1, we have that the limit of 1 over x as x approaches a is just equal to 1 over a. That's this part here. So it exists and in fact is equal to f of a. So that's 1 over a, provided that a is not equal to 0. All right, so now we're going to calculate the limit for these functions here. We want to find the limit of x minus 2 divided by x plus 1 as x approaches 1. So per the previous example we talked about and the theorem, what we can do now, notice that this function is continuous everywhere on its domain. So it's continuous for all real numbers. Notice that we don't have to, the only place it's not continuous is whenever we substitute in -1, because that'll make our denominator 0, but we don't care about that because our limit is approaching, we're concerned about the limit when x is approaching 1. So what we can do, we can just substitute in 1. So this is equal to 1 minus 2 divided by 1 plus 1, which gives us -1/2. So that is the limit as x approaches 1 of x minus 2 divided by x plus 1. Now let's find the limit as h approaches 0 of h squared plus h divided by h squared plus 2h. Well, notice that if you substitute in 0, you'll have 0 divided by 0. Well, that doesn't make sense. So we have to simplify this function a little bit algebraically before we begin. So we write this is equal to the limit as h approaches 0. We always write the limit until we evaluate. And then we write, our numerator has an h in common, so we can factor it out. So you have h times h plus 1, and then divide that by h times h plus 2, because the two terms in the denominator had an h in common. Now cancel your h's, and this is equal to the limit as h approaches 0 of h plus 1 divided by h plus 2. And now whenever you substitute in 0, you do not have a problem. Your function is continuous there, so we're good to go. So we get 0 plus 1 over 0 plus 2, which gives us 1/2. Awesome. So a fact is if f of x is equal to g of x for all x except possibly x equals a, then it turns out that the limit of f of x as x approaches a is also equal to the limit of g of x as x approaches a. So if the two functions are equal for all x except possibly at x equals a, then the limits of those two functions as x approaches a have to be the same as well. And now, let's shift that up too. And now theorem 2 says, if f of x has the form of this n degree polynomial over this mth degree polynomial, that with ci and di constants, and cn is not equal to 0 and d sub m is not equal to 0, so the leading coefficients here are not 0, then the limit of f of x as x approaches plus or minus infinity is equal to the limit of cn x to the n over dm x to the m as x approaches plus or minus infinity. So it's saying that all we really need to do is pay attention to these leading terms here. So as an example, let's calculate the limit as x approaches infinity of 6x squared plus 5x plus 100 divided by 3x squared minus 9. So according to this theorem, we pay attention to the leading coefficient, so we write this is equal to, remember you write the limit until you actually evaluate. So you have the limit as x approaches infinity of 6x squared divided by 3x squared. Your x squareds cancel, so that's the limit as x approaches infinity of 6 over 3, which is in fact equal to 2. There you go. So we've calculated the limit of that function as x approaches infinity. A few more examples just so you get the idea of what's happening here. Let's move this down. Part B, similar idea, except for now we are evaluating the limit as x approaches negative infinity of, and move it down, of 2x to the fourth plus 20x cubed divided by 1000x cubed plus 6. So this is going to be equal to the limit as x approaches negative infinity of 2x to the fourth divided by 1000x cubed. So that's equal to, notice that the x cubed cancel out with 3 of the x's on the numerator, so it leaves us with an x. So this is the limit as x approaches in negative infinity of x over 500, because 2 goes into 1,500 times. So as x approaches negative infinity, notice that this number here is going to be getting large but in the negative direction. So our answer here is just negative infinity. Okay? Great. So our last example for this section with limits from the algebraic viewpoint, we want to identify all singular points and points of discontinuity of the functions given. First, the function we're considering is f of x equals 2 divided by x squared minus 9. So notice that this is defined for all x except at x equals plus or minus 3. And it's not defined at plus or minus 3 because whenever you substitute those values in, it makes your denominator equal to 0, and we cannot divide by 0. So that means that x equals negative 3, and that means that x equals 3 are singular points. They are singular points. Okay? So notice that that just means, that is, they're isolated points at which the function is not defined. Okay, so those are our singular points. So that's our answer here. Okay, and now in the last example, you'll see ideas like this again. So make sure you review this and do their homework problems from this section. So we need to identify all the singular points and points of discontinuity for this piecewise defined function f of x equals 1 minus x if x is less than or equal to 1, x plus 2 if x is between 1 and 3 but not equal to 1 and 3, and x squared minus 4 if x is greater than or equal to 3. So here we have to do a little bit more work. So the only possibilities, so note that the only possibilities are at x equals 1 and x equals 3. Those are the only possibilities. So when you have a piecewise defined function, you have to pay attention to these values because they give you your only possibilities for your singular points or your points of discontinuity. So now we have to make sure we check the left and right hand limits at those values to see if the limit exists. So we have the limit of f of x as x approaches 1 from the left, and then we need to look at the limit of f of x as x approaches 1 from the right. So notice that the limit of f of x as x approaches 1 from the left, you look up here in the first part of your piecewise defined function and you have x is less than or equal to 1. That means if you're on a number line, if you're thinking about it, you have 1, you have 3, and as x is approaching 1 from the left, you're less than or equal to 1. So we're in this part of the function, which means we substitute 1 in here. You would get that's equal to 1 minus 1, which is equal to 0. As x approaches 1 from the right, notice that we are in the second part of the function. So that would be equal to 1 plus 2, which is equal to 3. 0 is not equal to 3. The left-hand limit is not the same as the right-hand limit. So that means that the limit of f of x as x approaches 1 does not exist. Remember, the left-hand limit has to be the same as the right-hand limit for the limit to exist at that value. So since it does not exist, we can say that there is a discontinuity at x equals 1. Okay? Now we check the limit, the left-hand and right-hand limit at 3. So the limit of f of x as x approaches 3 from the left, that's going to be equal to, notice that we're in this part of the function still, so that's equal to 3 plus 2, that's equal to 5. And then the limit of f of x as x approaches 3 from the right, what part of the function are we in? We're in the second part, or the third part. This is the third part, not the second. So we substitute 3 in here. That gives us 3 squared minus 4. 9 minus 4 is 5. Perfect, because that gives us the same value for the left and right hand limit, which means the limit of f of x as x approaches 3 is actually equal to 5. So these agree. So f is in fact continuous at 3. So that concludes our section. If you have any questions, make sure you send me an email or make sure you prepare for class on Tuesday. Have a good one.